Here's problem 12.2. An 80-kilogram man is 1/4 of the way up a 10-meter ladder that is resting against a smooth, frictionless wall. If the ladder has a mass of 20 kilograms and it makes an angle of 60 degrees with the ground, find the force of friction of the ground on the foot of the ladder. First thing we want to do for this kind of problem is make a free body diagram. So let's imagine a wall and a floor, and we have a ladder against this wall at a 60-degree angle, and we want to label all the external forces acting on the ladder. Well, it's got weight, and that's acting at its center of mass. So we have the weight of the ladder pulling down like that. We have a man who has walked up 1/4 of the way up the ladder, and he's got weight. So we have a force equal to the weight of the man acting like that. We have a force of the wall on the ladder. Now the wall is said to be smooth, which is redundant with frictionless. If we see the word smooth, we assume we go all the way to the point of calling it frictionless, which means that there would be no transverse component of the wall on the ladder. There would only be the normal force of the wall on the ladder. So we would have a normal force, which I'm going to call P, pushing on the ladder perpendicular to the surface of the wall, but there's no transverse component. And then we have a reaction force of the floor on the ladder, and we don't know what that is, but I'm going to say we have a vertical component and a horizontal component to that force. Not knowing what it is, but I know my horizontal component should be going to the right because my P force is going to the left, and I need something to balance those two forces so that they add up to 0 because I have no net force in the x direction. In fact, we can write that as the summation of the forces in the x direction is 0, and that should be equal to h minus p as we've drawn it. So in terms of magnitude, h will be equal to p. The horizontal component of that reaction force at the pivot will equal this pushing force p. Now actually, that horizontal component actually will be the frictional force of the ground on the ladder. So that's what we want to find. We want to find h, but if I can find p, then I will find h. So an equivalent way of doing this is to figure out what p is. At this point, we don't know 3 of these forces. We don't know h, we don't know the vertical component v, and we don't know what p is. And we want to find one of them. The best way to go is to figure out torques. Now, I have 2 best choices for my axis. I can choose A or choose B. And I want to make the choice that will eliminate the most possible forces of which I don't know. If I choose point A, then I can eliminate trying to find V and trying to find H because their line of actions go through point A, and that gives them no moment arm about that point. So that's actually a good way to go. If I choose point A, then I only have to worry about the moment arms due to the weight of the man, the moment arm due to the weight of the ladder, and the moment arm due to the P force on top. I need to find the distance to those line of actions, which would be the moment arms for those respective forces. Well, if I'm looking for the moment arm to the weight of the man, that would be this distance right here from the pivot to that line of action, and that distance, that's called D1, is going to be equal to the hypotenuse of that little triangle, which will be 2.5 meters, which is 1/4 of the way up the ladder, times the cosine of 60 degrees. Cosine of 60 is 1/2, so that gives me 1.25 meters. I also want to find the moment arm for the weight of the ladder, which is this distance here. Let's call that D2. And that's going to be 5 meters times the cosine of 60. And that will be 2.5 meters. Okay? And I need to find the moment arm to force P, which will be the shortest distance from the pivot to the line of action of that force, line of action being this right here, and that's going to be equal to the total length of the ladder times the sine of 60. So D3 is going to be 10 times the sine of 60. Sine of 60 is 0.866, so this is 8.66 meters. So that's that distance there. All right, now we have our 3 moment arms. We also need to know the weight of the ladder, which is the mass of the ladder times G, and that's going to be 20 times 9.8, 196 newtons. And I need the weight of the man, which is the mass of the man times G, which would be 80 times 9.8, 784 newtons. Okay, so we got our weights, we got our moment arms. Let's clear this off. Let's do a torque diagram. Here's point A. I've got a moment arm to force P, and that moment arm is 8.66 meters. I've got another force over here, the weight of the ladder, which is equal to 196 newtons, and the moment arm to that is 2.5 meters. And then I have another weight, if I can get this to cooperate, and that's the weight of the man, which is 784 newtons, and that has a moment arm of 1.25 meters. Now, as I'm looking at these weights and moment arms, the force P is trying to make this thing rotate about point A in a counterclockwise direction like this. That would be a positive torque by the right-hand rule. If I were to curl my fingers in the direction counterclockwise about point A, my thumb points out of the page in the positive Z direction. So that is a positive torque. The weight of the man is trying to make this thing rotate around like this in a clockwise direction. That will be a negative torque by the right-hand rule. If I curl my fingers in that direction, my thumb points into the page. And same thing with the weight of the ladder. That's trying to make this thing rotate counterclockwise as well. That will also be a negative torque about point A by the right-hand rule. So I have 2 negative torques, 1 positive torque. The thing's not rotating at all about point A, so the net torque should be 0. So let's set that up. We'll say that the summation of all the torques about point A is 0. And we do have torques. We have a positive torque, which is 8.66 times P, moment arm times force. And then we have 2 negative torques. We have a 2.5 times the weight of the ladder. And then we have a minus 1.25 times the weight of the man. Alright, so I have that 8.66 P is equal to 2.5 times the weight of the ladder, 196 newtons, plus 1.25 times the weight of the man, 784 newtons. So P is equal to all that, 2.5 times 196 plus 1.25 times 784 is 1,470 divided by 8.66, and I get 169.7 newtons. So that is the force of the wall on the ladder. Nice to know. I've always wanted to know that, but we want to find the frictional force of the ground on the ladder. But we already proved that the horizontal component of the ground on the ladder is equal to P, and that is our frictional force of the ground on the ladder. So that is equal to 169.7 newtons, and that is the force that we want. So the frictional force of the ground on the foot of the ladder is 169.7 newtons.